Features of this video. It reads 102 sine wave values through the I2C bus, writes the data to a file, and then plots the data using Octave. This is an extension of the previous YouTube video. Please watch R20162 first. Obviously, Octave had to be installed on the Raspberry Pi. The C program is similar to the one in the R20162 video. Input channel 0 is used, reference single-ended. 102 samples are read. 1 kHz I2C clock rate is selected. All 102 A to D bytes are read continuously. A file pointer is defined. A for loop processes each of the data values. Each byte is moved into an integer. The voltage is calculated for each integer. Each voltage is written to the file. The file is closed and the program ends. An Octave program running on the Raspberry Pi plots the data. This is for 307 Hz sine wave. The same data plotted on the remote terminal. As the sine wave frequency increases, the number of data points per cycle decreases. Here's a calculation predicting the number of data points for a 1 kHz sine wave. The I2C bus transfers 100,000 bits per second. 9 bits are required for each voltage sample. The time for one cycle of a 1 kHz sine wave is 1 millisecond. Unit analysis shows how to construct the formula for the calculation. 11 points per cycle can be expected for the 1 kHz signal. So here is the 1 kHz sine wave. This is the Octave program running on the Raspberry Pi that made these plots. This is the directory containing the Octave script or program. These two lines permit the script to be run from the command line also. The number of data values per second is calculated. The time for each data value is calculated. The data file is loaded into the local vector z. T is the vector of integers starting from 0. T becomes a time for each data value. The prime means transpose. Whos lists all the variables in the Octave workspace. This plots the voltage versus time, and plot labels and grid lines are added. Plots are smooth for frequencies less than 1 kHz.